So, in discussing light, electromagnetic radiation, remember that it's electric and magnetic fields. And so, if we imagine we got an electric field like that, okay, then where the electric field is up, if the light's going to the right, then that means magnetic fields out of the board, into the board, out of the board. Okay. Well, yeah, that's true, but we could have also had magnetic field like that. And then electric field would have been into the board, out of the board, into the board, out of the board. So that's the same thing. That all that I've done there on the right is I've taken what's on the left there and I've rotated it 90 degrees. So I've rotated it so the top of the wave is tilting away from you, and the electric field and the magnetic field that was coming towards you is tilted upwards. So I've just rotated by 90 degrees. It's still light. It's just a different orientation of light. The electric and magnetic fields are perpendicular to each other, to the first case. So this is what we call polarization. The polarization is the orientation of these electric and magnetic fields. They're always perpendicular to each other, but how are they oriented in space? And so we got polarization. Now, what happens is that different materials interact differently with light. So, for example, you could have material that has long conducting chains of molecules. And so an electric field parallel to that chain of molecules could cause electrons to run up and down the chain of molecules. If that happens, then the electric field is going to be absorbed. Well, that means that's if you get rid of the electric field, you get rid of the magnetic field, you stop the propagation of light, so the light's absorbed. On the other hand, if it's perpendicular to that, then the electric field doesn't make the electrons run, and it keeps going. And so what would happen is if I have a material that's oriented so only electric fields that are vertical go through there, light coming through here has electric fields in all different orientations. After it goes through, all the electric fields are vertical coming through. And so that means that this device or this material, because it can be just a simple piece of material, is what we call a polarizer. Okay. Now, interesting thing here about polarizers. Okay. And that is that a polarizer can then be placed over here. Now, if all the electric fields are vertical here, only the horizontal electric fields go through, so nothing goes through. So that means it would block the light. On the other hand, if I had the other polarizer like that, then the light would keep on going through because it's already permitting vertical polarization light to go through. And so what we have is a way of blocking light. We use this sometimes to make displays. For example, if you look at an LCD display, the electric field actually orients the crystal and aligns it up one way, and that polarizes things. Then what you do is you have another polarizer, and if you want it to be black, then what you do is you take the LED and you put an electric field on it, and what that does is it makes the electric field that goes through one way, and then the polarizer blocks it. And so you turn off the electric field, and the crystal will reorient itself, and then now light goes through again. So that gives you, whenever you have the electric field turned on, it makes it black. And the other thing that happens is, one thing you discover is that light, when it reflects off a surface, can sometimes come out polarized. And so you can use a polarizer as sunglasses that block that reflected glare. We'll talk more about light by polarization by reflection later. But Polaroid sunglasses are actually polarizers. And so if you use a Polaroid sunglass and look at an LCD display and then you rotate the display, you'll notice it's sometimes black and sometimes not. And that's because of that orientation that's in there. Okay. So what if we have unpolarized light? It goes through a polarizer that only allows vertical light to go through. And then we have another polarizer that's at some angle theta right here. Well, what happens is that some component of this light is parallel to that. The component that's parallel to it is going to be related to cosine theta. So the electric field here that's parallel is E cosine theta. And so what happens is that if you've got light that has a certain polarization, let's say vertical polarization, you have a polarizer tilted some angle theta right here, then the electric field that comes through, now the electric field that comes through is going to have the polarization there. So you've actually changed the polarization of it, but what happens is this electric field, if this is E naught over here, that's E naught cosine theta. Well, we know that intensity is related to the amplitude of the Poynting vector. And the amplitude, the Poynting vector, we also know is going to be E RMS squared over C mu naught. Okay, so what that would mean is that the intensity would be, this is my E, so the intensity on one side would be that, the intensity on the other side would be E naught cosine squared. And so we could then say that if this over here has some intensity, I naught, then over here, this intensity, if this is tilted by some angle theta, this intensity is going to be I naught cosine squared theta. And so this is this relationship right here, that the intensity after you go through a polarizer is I naught cosine squared, is called Malice's law. Okay, so let's do a couple of examples here. So let's imagine that we have completely unpolarized light, and it's shining here completely unpolarized on a polarizer. And let's say that the initial intensity is going to be equal to 1.25 watts per square meter. Now, when it goes to the polarizer, I want to know what's that intensity. And then it goes to another polarizer here that's tilted 30 degrees. And I want to know now what's the intensity here. And then it goes to another polarizer over here that's tilted another 60 degrees from there. So that means it's 90 degrees total. And I want to know what's the polarization over there. So that'd be I3. Okay. So, well, what's I1? I1, well, the light here is every possible polarization. We're only allowing what's coming through that has the vertical component. Well, that means it's all the vertical light, but any other light that's not vertical, the component that is parallel to that vertical will go through. Well, that ultimately means is it's going to be half of what originally it was. So I1 is going to be half of 1.25. So half of 1.25 is 0.625 watts per square meter. Now the question is, what about I2? So we want to figure out I2 now. So I2 is going to be I1 cosine squared of 30 degrees. Well, I1 is 0.625 watts per square meter, so all we have to do is multiply by the cosine of 30 degrees squared, and so that comes out to be 0.469 watts per square meter. So what about I3 over here? Well, I3 is going to be I2 cosine squared 60 degrees. And so I3 will be the 0.469 times the cosine of 60 squared. And so that's going to be equal to 0.117 watts per square meter. Okay. So now we have the initial intensity, have the intensity going through the first one, intensity going through the second one, intensity going through the third one. By the way, the first one is often called a polarizer. The others are sometimes called analyzers, even though they're exactly the same thing. So the analyzer is exactly the same thing as a polarizer. It's just a polarizer that is being used on already polarized light. Now let me point out something else here. We know that cross polarization like this on the right versus the one on the left should give you 0. In fact, if I did not have this in between polarizer in there, or analyzer, we would get 0 intensity at the end. But because that in between one changed the polarization and made the polarization something different than it was before, the new polarization in here actually has a component that is parallel to that last one. And that would not have been the case if we had not had that center one in there. So this is an example of where that center one has changed the polarization. Simply by measuring it and finding out what it was, we've changed what it was. We've changed it to a new polarization. Now that turns out to be an interesting thing that comes back later on in quantum physics, that by measuring something, you change it. So, but that's beyond the level of this class.